Number one. Did this start recording? Yeah, it did. Okay. All right. So, first question. So we're here. The information we're given here. We have a wide beam of white light, incident perpendicular to the surface of oil. Okay. An observer looking down at the film sees green light that has a maximum intensity. So we're given information about wavelength. Green is 520 nanometers, 5.2 times 10 to the negative 7 meters. Okay, the index of refraction of the oil, N equals 1.7. Now, first question, calculate the speed of the light inside the film. So here's what happens. So I'm going to draw a normal line to this boundary. So this is a thin film. This is a thin film problem, isn't it? Let's see.
Yeah.
Yeah. So here's what happens. So we have this ray that comes in like this. This white light goes bam, strikes the surface. Some of it reflects, and then some of it refracts, like that, and then reflects again. It comes up like this, and then refracts again, and those are going to be parallel. So that's kind of a setup here. Now, A, first question, calculate the speed of the light inside the film. So to do this, you use the definition for index of refraction. N equals C over V. So V is going to be C over N. C is a constant, 3 times 10 to the 8th meter per second. N inside the oil is 1.7. So we get a speed of 1.76 times 10 to the 8th meter per second. Hmm? Oh yeah, we're going to get to that. We're going to talk about phase changes in a minute. Okay, B, calculate the wavelength of the green light within the film. Okay, so we're focusing on, this is white light. The problem tells us that this ray here is white light. But remember, what is white light? It has all the colors of the rainbow. But the problem is focusing in specifically on the green. We're focusing specifically on the green that's within the white light. So if the wavelength is this in air, how do we find the wavelength of that same ray inside the oil? Because the wavelength is going to change. So here's how you do part B. You go N1, wavelength 1 equals N2, wavelength 2. Where did I get that equation from? It basically comes from this equation, and velocity equals wavelength times frequency. If you substitute these two equations together, you get this equation right here. Now, N1 is air, which is 1.00. N2 is the oil. So N1 will just set equal to 1, and we're solving for wavelength 2. So this will be wavelength 1, this is wavelength 2. Wavelength 2 is going to be wavelength 1 over N2. So this is 5.2 times 10 to the negative 7 meters over 1.7. So as you would expect, the wavelength gets smaller, because when the wavelength gets smaller, that's what explains the ray slowing down. So wavelength 2 comes out as 3.06 times 10 to the negative 7, which is 306 nanometers. Okay. Part C, calculate the minimum possible thickness of the film necessary to see the green light at maximum intensity. Yo.
For B, could you also use velocity of wavelength times frequency to find the frequency before, while it's in air, and then just use the same frequency?
Oh yeah. Are you saying this? So look, hey, good job. What you could do, so we now know the velocity in the oil, right? So you could just go velocity equals wavelength times frequency. And remember, what stays constant from one medium to the next? Frequency. The frequency here is the same as the frequency here. So if you find the frequency in air, it's the same as the frequency in the oil. Is that what you're saying?
Yeah.
Yeah. And then just solve this for wavelength, because you have the velocity, right? But it's pretty, actually what you're saying, it's the same thing as doing this.
Okay.
It works out to be the same, but yeah, that's totally fine. Okay, so this third question, we're looking for the thickness of the film. Now, this is thin film interference. The thing to know about thin film interference is when a ray strikes a medium that has a higher index of refraction, it has a phase change. So this ray right here that came in, it's coming in at 1.0, index of refraction is 1.0. The oil is 1.7. So this guy is going to have a phase change, right? Now what does a phase change mean? A phase change, if you have this wave, you know, it's wave-like, the light is wave-like. Let's say like right here is the boundary. A phase change is when a peak suddenly becomes a trough. A peak shifts to a trough. So the wave literally is like, there's a change of phase right at the boundary. Now, does this guy, so then this ray keeps going, right? He comes in, is there going to be a phase change at this boundary? No, there's no phase change there. Bam, like this, and he comes back, and then now is parallel. So this guy had no phase change. So we want these two rays reading the question. The question says, calculate the minimum thickness of the film necessary to see green light at maximum intensity. So if your eyeball is up here, here's your eyeball. If you're going to see a bright spot down here, should these two rays be in phase or out of phase? In phase. But this guy had a phase change, and this guy did not have a phase change. Can we get this guy to have a phase change? Can we make this guy have a phase change? No. Yeah. What's the other way to do it? The thickness of the film. So if we say that the thickness of the film is D, let's say the thickness of the film is D, what's the path, what's the extra distance that this guy traveled, approximately? 2D. 2D. So we're going to say 2D, which is, you know, he goes boom, boom, right? Down, up. We're going to approximate that to 2D. In order for this ray to be with this ray in phase, should the extra distance traveled be equal to one whole wavelength? No. Or should it equal a wavelength over 2? Wavelength over 2, right? That's the equivalent to a phase change. So if we do that, if we say, okay, the extra distance traveled is going to be equal to wavelength over 2, that's the equivalent of giving this ray a phase change. So then they both had a phase change, which means that they will be together. So now we can solve for D. So D works out to be lambda over 4. So we take the wavelength in the film, not this wavelength, right? We don't want that one. We want the wavelength that was in the oil. So it's going to be, what was the wavelength? It was let's just go in nanometers, 306 nanometers. That was the wavelength in here, 306. And then divide by 4, and that gives us 76.5 nanometers. Now, D. Recalculate part C for a situation where the oil is on top of diamond. Oh, man. Okay, so here, now instead of this being air, the oil is now on top of diamond. So how is this going to change everything?
You can steal it.
It's going to be a phase change. It's going to be like this. So the ray comes in like this. Bam. So air is 1.00. The oil was 1.7. And then diamond is 2.4. Okay, so this guy reflects off like this. Bam. Is that a phase change? Yeah, this guy has phase change. Then he goes bam like that, bam like that, boom like that. Now, down here, was there a phase change?
No.
Yeah, because it's 1.7 and 2.4. Whenever you reflect off of a medium with a higher index of refraction, you get a phase change. So now, to get a bright spot, so here's D, right? So what's the extra distance traveled? 2D. Now, they've both had a phase change. So now this is just going to be lambda. Like if you're looking down on this, if that's your eyeball, you want these to stay in phase, so that's just going to be lambda. So D is going to be lambda over 2. So this is going to be 306 nanometers over 2. So this is 153 nanometers. Okay?
Did you not have to solve for a new lambda?
No, because the wavelength in the oil is still the same. It's still well, no, because it's not going into the diamond. Like what we considered here never actually.
It just has another phase change.
Yeah, all that matters is that you had a phase change right on that boundary. Okay, the oil film now rests on a thick slab of glass with an index of refraction of 1.4. So now we got a whole new setup here. So here's the new setup. We got these boundaries. Air, glass, oil, air, like that. And all the indexes is n equals 1.0, n equals 1.7, n equals 1.4, it's a 4, n equals 1.0. Okay, a light ray is incident. Okay, sketch the path. Ooh, easy, dude. This is like Chillsville. Bam. So, okay, what's this guy going to do? Going from smaller index to larger index, he goes which way? Towards the normal. Bam, like that. And then, boom, now what's going to happen here? He's going from bigger index to smaller index. He goes which way? Away from the normal. But still not parallel to that guy. Right, that would only be if this, so, gee, this is kind of hard to draw. So hold on, let me back this up. Let's exaggerate this. Boom, so he comes in like this. So that's going to be a pretty big bend. Boom, like that. This would be better. Like that. But then this guy's going to go away from the normal, but still not parallel to that guy. Right, like that. Okay, then this comes down like that. And then into air. So which way is it going to bend? Away from the normal. Oh, and then these are going to be parallel.
Yeah.
This and that should be parallel to each other. Because this is 1.0 and that's 1.0. Okay. And then you know what? You should show reflection too. But the question is, where would you stop showing that? I would just show reflection at those boundaries like that. Okay. Referring to the diagram above, at which boundary is it possible for total internal reflection to occur? Where could total internal reflection occur? Total internal reflection can only occur from when a ray is trying to go from higher index to lower index. So it could occur here and then here. Those are the two possible places it could occur. For each identified boundary, calculate the critical angle. So the equation for critical angle, you can derive it from Snell's law. N1 sine theta 1 equals N2 sine theta 2. So the whole idea, let me just sketch in. This is like a review of total internal reflection. The whole idea with total internal reflection is if you have this, let's say this is like a block of glass right here. So look, you're looking at a ray that's trying to come out of a glass, like that. So here's the boundary. What's the maximum it could refract? 90. The maximum refraction is 90, and what do you call this angle when that happens? The critical angle. So theta 1's the critical, theta 2 is 90. 90, what's sine of 90? 1. So what we're left with is sine of the critical angle is N2 over N1, where N2 has to be smaller. So how do you find critical angle for this boundary right here? You're going to go sine of critical equals 1.4 over 1.7, right? This would be N2, this would be N1 for that boundary. Okay, how about for this boundary right here? Well, this would be N2, and this would be N1. So for this calculation here, you're going to go sine of critical angle equals 1.0 over 1.4. The critical angle at that boundary is 45.6. And then at this boundary, it's 55.4. Wait, did I switch those? Are those backwards? No, those are right.
Yeah, that's right.